Hello everyone. Here I am going to give a lecture about multi-earth reading. This is chapter number 26, and this will be my third lecture. The multi-earth reading. The topic is all about performing an action at a time with multiple tasks. Here it says about performing an action completely at a time. It will be nice, and it will be very precise work. But nowadays only one action can be performing in any computer is not, it is not so worth it. So the supercomputers have been designed to perform n number of actions at a time. Like multitasking, compiling a program, sending a file, and receiving electronic mails. These all actions can be done at a time concurrently. Only computers can be doing multiple tasking, can be done by multiple processor, which leads to make the work done so easily. Computers too can perform operations concurrently. It is common for personal computers to compile a program, sending a file to a printer, and receiving electronic mails over a network concurrency. Only computers that have multiple processors can truly execute multiple instructions concurrently. Operating systems on a single processor computers create the illusion of concurrent execution by rapidly switching between activities, but on such computers only can compile single instruction. Historically, concurrency has been implemented with operating systems primitively available only to execute system programs. The programming language, which developed by the Department of Defense, made concurrency primitives widely available to defend the contractors building military and command control systems. So here the introduction, it all says about performing an action, single action, which will be more precise, which will give you a more precise output, but comparatively doing n number of actions at a time will give the work done fastly, and it can be done precisely. And today's multi-core computers have multiple processors that enable computer to perform tasks consequently, like smartphones and latest computers. Concurrency has been implemented with operating systems. These relation can be understood only by experienced programmers. So the concurrency is nothing but doing an action, doing two or more events at a time. So these can be done. This concurrency is designed by an operating system. So this programming can be done by experts only. Coming to the Java concurrency, Java makes concurrency available to you through the languages and APIs. Java programming can have multiple threads of executions, where each thread has its own method called stack and program counter, which allows it to execute concurrently with other thread while sorting with them application wide resource such as memory. This capacity is called multi-earth reading. So the Java concurrency gives the brief description about multi-earth reading. It says Java programming can have multiple threads of executions, so it can execute multiple threads at a time, where each thread has its own method called stack and program counter, which allows it to execute concurrently with other threads while sorting with them application wide resources such as memory. Concurrent programming users, concurrently programming users will discuss many applications of concurrent programming. For example, when downloading a large file like image and an audio clip or video image over the internet, the user may not want to wait until the entire clip download before starting the playback. So to solve this problem, multiple threads can be used on to download the clip and another to play it. These activities proceed concurrently to avoid choppy playback. So here it says concurrent programming can be designed in such a way that a video will be downloading at a time, and at the same time the user can play back the video. So this will be happened by concurrent programming. To avoid the choppy playback, the threads are synchronized. That is, the actions are coordinated. So here this programming makes a choppy playback and threads to come to same path, so that the player thread doesn't begin until there is sufficient amount of clip in the memory to keep the player thread busy. The Java Visual Machine, this can be done by Java Visual Machine, and to run the program thread to perform a housekeeping task such as garbage collections. So that this is just an example for JVM. Concurrent programming is difficult, while writing a multi-thread program can be tricky. Although we can say human mind can perform a number of concurrency actions. So people find in difficulty to jump between the parallel trains of thought to see why multi-earth program can be difficult to write and understood. Try the following experiments. Open three books to page 1 and try reading the book concurrently. Read a few words from the first book, then a few from the second, then few from the third. Then loop back and read the next few words from the first book, and so on. After this experiment, you will appreciate many of the challenges of multi-earth reading, switching between the books, reading briefly, remembering your place in each book, moving book to you closely so that you can see and pushing the books you are not reading aside. So it is a saying about how a human mind can perform multiple tasks, and use the pre-built classes of the concurrency APIs whenever possible. Programming concurrent application is difficult and error prone. So programming application will be difficult, and it can strike many errors. If you must use synchronization in a program, you should follow some simple guidelines. Use existing class from the concurrency API such as array, blocking, query class we discuss in section that manage synchronization for you. These classes are written by experts, have been thoroughly tested and debugged, operated efficiently, and help you avoid common traps and pitfalls. If you need even more complex capabilities, you should interface lock and condition that we introduced in section. These interfaces should be used only by advanced programmers who are familiar with the concurrent programmers. Common trap and pitfall. They provide the uses of those. They provide solid basics for understanding how concurrent applications synchronize access to shared memory. The concepts are important to understand, even if an application does not use these tools explanatory. By showing you the complexity involved in using these low-level features, We hope to impress upon you the importance of using pre-built concurrency capabilities wherever possible. Coming to the thread stats life cycle of a thread. At any time, thread is said to be in one of several thread states used in UML state diagram. The UML state diagram, which looks like this is a UL. This is nothing but the state diagram. Here it says the life cycle ULM state diagram, and the new synchronized that it is a new thread. Program starts from the new thread and it goes to the runnable, and this runnable is connected to the waiting, time waiting, and terminated and blocked. We can see the links from here from runnable to notify variable wait, what stat, and so here it says a new and runnable state. A new thread begins in its life cycle in the new state. It remains in this state until the program starts the thread, which places in the runnable state. A thread in the runnable state is considered to be executing in its tasks. So here it says a new and runnable state. A new thread begins in the life cycle in new state and it remains in the state until the program starts the thread, which places in the runnable state. A thread is runnable state. Is considered to be executed in the task. So these were concerned of the task. Coming to the waiting state. Sometimes a runnable thread transitions to the waiting state while it waits for another thread to perform a task. A waiting thread transitions back to the runnable state only when another thread notifies it to continue execution. Time waiting state. Time waiting state says a runnable thread can be entered the time waiting state for a specified interval of time. It transactions back to the runnable state when the time interval expires or when the event is waiting for occurrence. Time waiting and waiting thread cannot be processed even if one is waiting there. So coming to the next one, which is a block state. Here block state says that runnable thread transition to the block state when it attempts to perform a task that cannot be compiled immediately, and it must temporarily wait until the task completes. For example, when a thread issues an input or output request, the operating system blocks the thread from executing until the input or output request completes. At the point the blocked thread transitions to the runnable state, so it can resume execution. A blocked thread cannot use a process even if one is available. So, and the terminated state, a runnable thread enters the terminated state, sometimes called the dead state, when it successfully compiles its task or otherwise terminates the perhaps due on an error. In the UML state diagram of figure 26.1, terminated state is followed by the UML final state. So this is the 26.1 diagram, and UML final state that pulls I symbol so indicates the end of the state transactions. Operating system view of the runnable state. Operating system view of the runnable state is shown in a figure. So this explains the operating system use of the runnable state. At the operating system level, Java runnable state typically encompassed to two separate states. The operating system hides these states from the Java virtual machine, which sees only the runnable state. When a thread first transitions to the runnable state, when a thread first transition to the runnable state, the new state in its ready, it will be kept ready for the next stage and keep running the first one. When the operating system assigns to a processor, also known as dispatching the thread. In most operating systems, each thread is given as a small amount of processor time called as quantum or time slice, with which to perform its task, declining how large the quantum should be in a key topic. An operating system occurs when its quantum expires. The quantum expires the thread return to the ready state, and the operating system assign another thread to the processor. The transaction between the ready and the running state and or another thread to the processor. Transaction between the ready and running state handled slowly by the operating system. The JVM does not see the transactions. It simplify views, and the threads are being runnable and leaves it up to the operating system to transaction. And the ready and runnable state will be dispatched. This section is known as thread scheduling and is dependent on thread priorities. Thread priorities and thread scheduling. This will be the next topic. Every Java thread has a thread priority that helps to determine the ordering in which thread are scheduled. Each new thread inherits the priority of the thread that creates it. High priority threads are more important to a program and should be allocated a process time before lower priority threads. Nevertheless, thread priority cannot guarantee the order in which a thread executes. So it all says about the thread can be executed, but it can't be shown that the output is in which thread. It recommends that you cannot create and use thread objects to implement concurrency, but rather use the executor interface, which is described in before topics. The thread class does contain some useful static methods, which you will use later. More operating systems support telescaling, which enable thread of equal priority to share a processor. Telescaling can be used to share the priority without time scaling. Each thread is a set of equal priority threads. To compile or get interrupted by the higher priority before other thread of equal priority get a chance to execute with time scaling. Even if a thread has not finished executing within the quantum expires, the processor is taken away from the thread and given to the next thread of equal priority if one is available. An operating system thread schedule to determine which thread runs next. One simple thread schedule implementation keeps the highest priority threads running at all time, and if there are more than one highest priority thread, ensures that all such threads executes for a quantum each in a round robin fashion. This process contains until all threads are run to compile. Creating and executing thread with executor framework. Creating concurrent tasks with the runnable interface. Implement the runnable interface of specify a task that can execute concurrency with other tasks. The runnable interface declares the single method run, which contains the code that defines the task that a runnable object should perform. Executing runnable object with the executor to allow a runnable to perform a task, you must execute an executor object execution. This is known as thread pool. When an executor begins execution runnable, the executor calls the runnable object's run method, which executes in the new thread. The execution interface declares a single method named execute which accepts a runnable argument. Using an executor has many advantages over creating threads. Executor can reuse execution thread to eliminate the overhead of creating a new thread for each task, and can improve performance by optimizing the number of threads to ensure that the process stays busy without creating so many threads that the application runs out of resources. Using class execution to obtain an executor service. The executor service interface executes the declaration various methods for managing the lifecycle of an executor. An object that implements the executor service interface can be created using static method declared in a class executors. We use interface executor service and a method of class executor in our example, which executes 3 tasks. Implementing the runnable interface, implementing the runnable interface in line 5. In the line 5, public class print task, implementing the runnable. So that is implementing the runnable interface so that multiple print tasks can execute concurrently. Variable sleep time in line 7. In line 7, private final int sleep time, that is a variable sleep time, stores a random integer value from 0 to 5. Second, create in the print task constructor in line 17. Sleep time will generate a next int which is given as 5000. Each thread runs as a print task sleep for amount of time specified by the sleep time. Then output its task name, and a new message indicates that it is done sleeping. A print task executes when a thread calls the print tasks run method from line 25 to 26. This is from line 25 to 26. System output print, which is given by the time and the task name. So that is line 5 to 26. And the line 27 invocates the static method sleep of the class thread to place the thread in the time waiting state of the specified amount of time. At this point, the thread loses the process and the system allows another thread to execute. So in the line 27 it says the thread sleeping time. This command is used to compile the thread sleeping time, and while the thread awakes it returns to the runnable state. When the print time is assigned to a process, again line 36 outputs a message indicating that the task is done sleeping. Then method run terminates the catch at line 29 to 33. Is required because method sleeps might show a checked expectation of type interrupted expectation in a sleep thread. Interrupted method is called. When the interrupted method is called, using the executor service to manage the threads that executes the print task. Use the executor service object to manage thread that executes the print task, and line 11 to 13 executes the print task. Here it is given as a public print task and string name, and the task name is equal to name. The catch at line 29 to 33 is required because the method is asleep might throw a checked expectation of a type interrupted expectation in a sleep thread, which is known as interrupted method. And the new catch thread 2 to obtain an executor service that's capable of creating a new thread as they needed by the application. These threads are used by executor service to execute the runnable. So here creating the execution thread with the executor framework. This is a whole code for the creating execution service in the execution framework. And string executor task starting the main ends. Here task 1 goes to the sleep for 4806 milliseconds. Task 2 go to the sleep for 2513 milliseconds. String executor. So the time elapsed to the task he has given. Line 21 to 23, each invoked the executor service executes the method. Invoked service executes the execution method. So from line 21 to 23, this is the invoked service which executes execution method, which is given by represented by execute task 1, 2, 3, and the runnable passes to each as an argument. Sometimes in the future the specified task may execute in one of the threads in the executor service. Thread pool in new thread created to execute it, or in the thread that call the execution method. The executor service manages the details. Method execute written implementally from each invocation. The program does not wait for each print task to finish. The line 26 call the executor service method known as shutdown. Line 20 execution service method 26 calls the thread executor dot shutdown. This is the execution method which calls the execution service, which notifies the executor service to stop accepting the new task, but continues executing tasks that have already been submitted. Once all of these previously submitted runnable have completed, The thread executor terminates and the line 28 outputs a message indicating that the task were started and the main thread is finishing its execution. Here on the line 28 it shows a thread is already started and main thread is in the execution. So here it says task started and main ends. So that is the code which represents like this. The code in main execution in the main thread, a thread created by the JVM. The code is run in the run method of the print task in the line 21 to 37. Executes wherever the executor states each print task. Again, this is sometimes after they pass it to the executor. When main terminates, the program itself continues running because there are still tasks that must finish executing. The program will not terminate until these tasks complete. The simple output shows each task's name and sleep time as a thread goes to the sleep. The thread which the shortest sleep time normally awakes first indicates that it is done sleeping and terminates in section. We discussed the multi-threading issue that could prevent the thread with the shortest sleep time from awaking first. In the first output, the main thread remains before any of the print tasks. Output their name and sleep times. This shows that the main thread runs to completion before any of the print tasks get a chance to run. In the second output, all the print tasks output their name, the sleep time before the main thread terminates. This illustrates the fact that we cannot predict the order in which the task will start executing, even if we know the order in which they were created and started. So after this coding, it shows that sleep time of the thread and executing time of the thread. So here in this coding, it is showing that it has created 3 threads, and we have given some codes by shutdown main, which will shut down all the 3 sets, 3 threads, and which will activate later. So to activate the thread, we need to give the system task started. This is a command which is used to activate the thread, and main ends. The main ends represents the previously executed thread will start the sleep time. And after this, coming to the thread synchronization, when multiple threads share a object and it's modified by one or more of them, indeterminate the results may occur, as well seen in the example before. Unless access to the shared object it managed properly. If one thread in the process of updating a shared object and another thread also tries to update it, it is unclear which thread is updating task effect. When this happens, the program behavior cannot be trusted. Sometimes the program will produce the correct result, and sometimes it won't. In either cases, there will be no indication that the shared object was manipulated incorrectly. The problem can be solved by given only one thread at a time execute exclusive access to code that manipulate the shared object. During that time, other thread desiring to multiply the object are kept waiting. When the thread with executive access is nothing but which I have shown in previous code in the line number 28. This process called the thread synchronization. coordinates access to share the data by multiple concurrent threads. By synchronizing thread in this manner, you will ensure that each thread accessing a shared object execute all other threads from doing a simultaneous work. This is called a mutual execution. Monitor. A common way to perform synchronization is use Java built-in monitors. Every object has a monitor and a monitor lock or interactive clock. The monitor ensures that its object monitor lock is held by maximum of only one thread at a time. Monitor and the monitor locks can trusted by using the enforce mutual execution. If an operation requires the execution thread to hold a lock while the operation is performed, and thread must accurate the lock before the synchronization happen. To specify that a thread must hold a monitor lock to execute a block of code. The code should be placed in the synchronizer statement. Such code is said to be guided by the monitor lock. A thread must acquire the lock to execute the guided statement. The monitor allows only one thread at a time to execute the statement within synchronizer state, and which is given by only one thread at a time can hold the monitor lock. The synchronizer statement are declared using the synchronizer keyword. The synchronizer keyword is a synchronizer keyword will be like a synchronized object statement and end synchronizer statement. This is if a code is given like this, it represents to end the synchronization and run the new thread. Where object is whose monitor logged is accurate. While coming to the next one, unsynchronized data sharing. First, we illustrate the danger of sharing an object across threads without proper synchronization. In this example, two runnable maintain references to a single integer array. Each runnable write 3 values of the array, then terminates. This may seem harmless, but we will see that it can result in error if the array is manipulated without the synchronization. Coming to the class array writer, implements the interface runnable to define the task for interesting value in a simple array object. The constructor line will be from 10 to 14. So this is the constructor line, which is from 10 to 14. Here it gives an int value and a simple array value and state value. Class which takes 2 arguments and an integer value. Within the first value, this task will insert in a simple array object and refer to the simple array object in the line 20. Invokes the method add on the simple array object. The task completes after the 3 consecutive integers beginning with the start value are added to the simple array objects. Coming to the class shared array test. Class shared array test executes 2 array writer tasks and add value to the single simple array object in line 12. Line 12, it shows the state value is equal to value, that is a single simple object, contains a 6 element simple array object. Line 15 to 16 creates the two new array writer task. On the plain value will be 1 2 3. The simple array object and one that plays value will be 11 to 13 lines. 19 to 21 creates a executor service and execute the two array writer. And the line 23 will be invokes the executor service shutdown method to prevent the additional task from the starting and to enable the application to terminate when the currently executing task. Recall that executor service method shutdown returns immediately. Thus, any code that appears after the call to executor service method shutdown in line 23 will be continue executing as long as main thread is still assigned to a processor. We would like to output the simple array object to show you the result after the thread compile their task. So we need the program to wait from the thread to compile before main output simple array object which interface executor service provides the await termination method. For this purpose, the method returns control to its caller either when all the task executes in the executor service complaint or when the specified timeout elapses. If all tasks are completed before awaiting termination timeout, this method returns true. Otherwise, it returns false. The two arguments to await termination represent a timeout value and a value of measure specified with a constant from class time unit. In this class, the time unit minute. In this example, if both tasks compile before awaiting termination timeout, and the line 32 displays the simple array object content. Line 32 displays the simple object compiled. Otherwise, in line 34 to 35, print a message including that the task did not finish executing before awaiting termination timeout. The output in figure 27 demonstrates the problem highlighted in the output that can be caused by failure to synchronize access to shared data. The value 1 was returned to eliminate 0, that then overwritten later by the value 11. Also, when the writer index was incremented to 3, nothing was written to that element as indicated by the 0. In that element of the printed array, recall that all we added calls to thread and which continues the sleep method operation on the shared data to emphasize the unpredictable of thread scheduling and increase the likelihood of producing errors output. Even if this operation was allowed to proceed to their normal place, we should still see the errors in the program output. However, methods caused by two threads executing this method concurrently, even if we tested the program dozens of times. On this challenge of multi-headed programming is spotted, will be spotting the errors. They may occur so interfrequency that can be broken the program, which doesn't happen. So this is multi-headed programming code. this is the sleep time of the pool thread 1, which will be 1 to element 0, and the next return index 1, and pool thread row 2 and which will be element 1, which is shown like a first pool is one thread and 1 wrote the value and 1 to element 0 later pool. Class simple array with synchronization. Simple array with the proper synchronization. Notice that it is identical to the simple array which is in the class of figure 26.5, which is shown in previous code. Expect that add is now synchronized. In the method line 20, so add is now synchronized, which is represented by public synchronization void add and int value. Which expect that add is now synchronized, so only one thread at a time can execute this method. We reuse the classes array writer and synchronizer arrow test from the previous example. In the line 20 declares the method, so synchronizer making all of the operations in this method behaves as a single atomic operation. In line 20 it says all operations behave as a single atomic operation, which is called as public synchronized void add, and it will be int value. Line 22 performs the first sub operation stored the value of writer index. The line 35 defines the second subordination, writing an element to the element at the index position. In the line 39 increments the writer index when the method finishes the execution at line 41. The executing thread implicitly releases the simple array lock, making it possible for another thread to begin executing the add method. In the synchronizer add method, we print message to the console indicating the progress of thread as they execute this method. In addition to perform the actual operations request to insert a value in the array, we do this so that the message will be printed in the correct order, allowing us to see whether the method is properly synchronized by comparing these outputs with those of our previous unsynchronized example. We continue to output message from synchronized block in later examples for demonstration purpose. Typically, however, input should not be performed in synchronized blocks, because it is important to minimize the amount of time that an object is locked. Also, line 27 in this example call thread method as sleep emphasizes unpredictability of thread synchronization. You should never call sleep while holding a log in a real application. Keep the duration of synchronized statement as short as possible. While maintaining the needed synchronization, this minimizes the wait time for block thread, avoid per formation input, lengthy and calculated and operating that do not require synchronization while holding a lock. Another note on the thread safety. We have said that it is necessary to synchronize access to all data that may be shared across multiple threads. Actually, this is a producer-consumer relationship blogging query. One way to synchronize the producer and consumer thread is to use the class from Java concurrency packing. that encapsulate the synchronization for use. Java includes the class array blogging query, a fully implemented thread safe buffer class that implements the interface blogging. This interface executes the queue interface discussed in chapter 20, and and declares the methods, put and takes the blogging equivalent of queue methods offering and pull representatively. Method puts placing and implements at end of the blogging query waiting in the queue in full method. The take removes and implement from the head of the blogging queue. Waiting in the queue is empty. These methods makes a class array blogging query choice for implementing a shared buffer. Before the method put blog until there is room in the buffer to write a data, and method take blog until there is a new data to read. The producer must produce a value first. The consumer concurrently consumer only after the producing write a value, and producer correctly produce the next value for only the consumer read the previous value. Array blogging queue stores the shared data in an array. The array size is specified as an argument to the array blogging in queue constructor. One created an array blogging queue is fixed in size and will not expand or accommodate extra elements. The this demonstrates a producer and a consumer accessing an array blogging queue blogging buffer uses an array blogging initiating object that stores an integer line that creates an array blogging in queue process 1 to the constructor, which is shown in from line 7 to 11. This is from line 7 to 11. Blogging buffer implements the interface buffer and uses the class producer, uses the class producer and the customer. This approach demonstration that the thread accessing and sharing object are unaware that there is a buffer access are not synchronized. The synchronization is headed entirely in the set and get methods of blogging buffer by calling the synchronized array blogging queue methods put and take representatively. Thus, the producer and the consumer runnable are properly synchronized simply by calling the shared objects set and get methods. In line 17, the method set calls the array blogging queue object put method. This method calls the object if necessary until there is room in the buffer to place a value. Calls the array blogging queue objects which takes the method. This method called blogging. This method called blocks if necessary until there is an element in this buffer to remove the line from 18 to 19 and 26 to 27, which will be using an array blogging queue object and size method to display the total number of elements currently in the array blogging queue. Class blogging buffer test contains the main method that launches the application. Line 20 creates an executor service, and the line 15 creates a blogging buffer object and assumes its reference to the buffer variable shaded location. From line 17 to 18 executes the producer and consumer runnable. Line 19 calls the method shutdown to the end the application when the thread finishes the executing the producer and the customer task. So here it says from line 18 17 18, it says application execution, new producer, and shared location. And these are the producer writes and buffer cell copies, customer reads and buffer cell copies 0. So these are the relations between producer and the customer, and how the output of the buffer cells copies. While methods put and take an array blogging queue are properly synchronized, blogging buffer method set and get are not declared to by synchronized. Thus, the statement performing method set to put the operation in the line 17. Coming to the producer and consumer relationship with synchronization, the previous example shows how the multiple threads can share a single element buffer in a thread safe manner by using the array blogging queue class that encaptures the synchronization necessity. Can implement and share buffer yourself using the synchronized key, and methods of class object using an array blogging queue will result in more maintainable and better performing code. The first step in synchronizing access to the buffer is a implement method and get and set to an synchronized methods. When a method set and produce thread, when the producer threads run method invokes a synchronized method, set the thread implicitly attempts to the acquires synchronized set buffers. Object monitor lock. If the monitor lock is available, the producer thread is implicitly acquires the lock. Then the loop at a line 13 to 19 first determine whether occupies a true. If so, buffer is full. So the line 16 outputs a message indicates that the producer thread is trying to write a value, and the line 17 invokes method display state the line 56 to 60 to output another message indicating that buffer is full. Method to get and consumer thread. Methods get and set are implemented similarly. Whether the customer threads are run, method invokes a synchronization method get, and the thread attempts are to acquire the monitor lock on the synchronized buffer objects. If the lock is available, the consumer thread acquires it. Then the while loop at line 36 to 42. These are the consumer price and threads. So these are also consumer buffer is empty. Consumer where is the producer write to the buffer cell occupies 1. So buffer cell is 1, 2 and 1. Interface lock and class producer cell relationship lock and the condition interface. So the synchronized keyword provides for most basic thread synchronization, and it's a Java to produce our other tool to access in developing concurrent programming. In this section, we discuss that the lock and the condition interface. This interface gives you more more control over the synchronization but are most complicated to use. So it shows you like this, and this is all about the multi-threaded programming. Thank you. Producer-consumer relationship blogging query. One way to synchronize the producer and consumer thread is to use the class from Java concurrency packing that encapsulate the synchronization for use. Java includes the class array blogging query, a fully implemented thread safe buffer class that implements the interface blogging. This interface executes the queue interface discussed in chapter 20 and declares the methods put and takes the blogging equivalent of queue methods offering and pull representatively. Method put placing and implements at end of the blogging query waiting in the queue in full method. The take removes and implement from the head of the blogging queue. Waiting in the queue is empty. These methods makes a class array blogging query choice for implementing a shared buffer before the method put blog until there is room in the buffer to write a data, and method take blog until there is a new data to read. The producer must produce a value first. The consumer concurrently consumer only after the producing write a value, and producer correctly produce the next value for only the consumer read the previous value. Array blogging queue stores the shared data in an array. The array size is specified as an argument to the array blogging in queue constructor. One created an array blogging queue is fixed in size and will not expand or accommodate extra elements. This demonstrates a producer and a consumer accessing an array blogging queue class blogging buffer uses an array blogging initiating object that stores an integer line that creates an array blogging in queue process 1 to the constructor, which is shown in from line 7 to 11. This is from line 7 to 11. Blogging buffer implements the interface buffer and uses the class producer and the customer. This approach demonstration that the thread accessing and sharing object are unaware that there is a buffer access are not synchronized. The synchronization is headed entirely in the set and get methods of blogging buffer by calling the synchronized array blogging queue methods put and take representatively. Thus, the producer and the consumer runnable are properly synchronized simply by calling the shared objects set and get methods. In line 17, the method set calls the array blogging queue object put method. This method calls the object if necessary until there is room in the buffer to place a value. Calls the array blogging queue objects which takes the method. This method called blogging. This method called blocks if necessary, until there is an element in this buffer to remove the line from 18 to 19 and 26 to 27, which will be using an array blocking queue object and size method to display the total number of elements currently in the array blocking queue. Class blocking buffer test contains the main method that launches the application. Line 20 creates an executor service, and the line 15 creates a blocking buffer object and assumes its reference to the buffer variable shaded location. From line 17 to 18 executes the producer and consumer runnable. Line 19 calls the method shutdown to the end and the application when the thread finishes the executing the producer and the customer task. So here it says from line 17 18 it is application execution, new producer and shared location, and these are the producer writes and buffer cell copies, customer reads and buffer cell copies 0. So these are the relations between producer and the customer, and how the output of the buffer cells copies. While methods put and take an array blocking queue are properly synchronized, blocking buffer method set and get are not declared to by synchronized. Thus the statement performing method set to put the operation in the line 17. Coming to the producer and consumer relationship with synchronization, the previous example shows how the multiple threads can share a single element buffer in a thread safe manner by using the array blocking queue class that encaptures the synchronization necessity. Can implement and share buffer yourself using the synchronized key, and methods of class object using an array blocking queue will result in more maintainable and better performing code. The first step in synchronizing access to the buffer is a implement method and get and set to a synchronized methods. When a methods set and produce thread, when the producer threads run method invokes a synchronized method, set the thread implicitly attempts to the acquires synchronized set buffers. Object monitor lock. If the monitor lock is available, the producer thread is implicitly acquires the lock. Then the loop at a line 13 to 19 first determine whether occupies a true. If so, buffer is full. So the line 16 outputs a message indicates that the producer thread is trying to write a value, and the line 17 invokes method display state the line 56 to 60 to output another message indicating the buffer is full. Method to get and consumer thread. Methods get and set are implemented similarly. Whether the customer threads run, method invokes a synchronization method get, and the thread attempts are to acquire the monitor lock on the synchronized buffer object. If the lock is available, the consumer thread acquires it. Then the while loop at line 36 to 42. These are the consumer price and threads. So these are also consumer buffer is empty. Consumer whereas the producer write to the buffer cell occupies 1. So buffer cell is 1, 2 and 1. Interface lock and class producer cell relationship lock and the condition interface. So the synchronized keyword provides for most basic thread synchronization and it's a Java to produce our other tool to access in developing concurrent programming. In this section we discuss that the lock and the condition interface. This interface gives you more control over the synchronization but are most complicated to use. So it shows you like this, and this is all about the multi-threaded programming.